Hello all, today we are covering 6.3 binomial radical expressions. You guys will be able to add and subtract radical expressions by the end of this lesson. So we are going to start by reviewing what we had written down a couple lessons ago. We have our index, our radical sign, and our radicand. So we have like the square root or the cubed root or the fourth or fifth, anything like that. That would be shown in our index. Our radicand is a number or a variable or both. And then our radical symbol is our radical sign is what shows that it is a squared, a cubed, a root. So the idea of adding and subtracting means that we need like radicals. And like radicals have the same index and radicand. That means we need both our index and our radicand to match up to be able to do anything. So if you notice here, in our properties, our indexes match up, they're both n, and our radicands match up, they're both x. Now that's just a general form. We'll do some examples in just a minute. So this property, because our indexes and our radicands match up, we can just do a plus b times the nth root of x. Similarly with subtraction, we just take a minus p times the nth root of x. It's kind of like our grouping idea when we factor, where you just pull out the greatest common thing, in this case the nth root of x from both, and then you just finish out the rest. So example 1, part A, simplify if possible. Check your indexes, are they the same? In this case they're both square roots, so that checks out. Check your radicands, they're both 5x, so they're the same. We can go ahead and subtract the terms in front, and then you are left with just a 5x. That will then equal 1 square root of x, which is really just the same as square root of 5x. Okay? Simple as that. We do have another one. Check here. Check your indexes. Maybe I should make this a little smaller. Are the indexes the same? They are the same. The indexes are the same. They're both square roots again. But are the radicands the same? They are not. So in this case, we just say the radicands are different. You cannot combine the expression. Okay? And then the following one, check your indexes again. These ones are once again square roots. Our radicands are also the same, 7xy. So you can combine. Make sure you pay attention. Bring that x down. It's not a multiply, it's a variable. So 12x plus 8x all times 7xy. So we end up getting 20x square root 7xy as our answer. Okay? And then the next two, we need to simplify before adding or subtracting. Right now, our indexes match on part A, and separately, our indexes also match on part B, but our radicands are all different, meaning that currently we can't do anything with them. But if we simplify before adding and subtracting, we can do some things. So This just means we need to do our factor trees. So I factor tree these out. Whoops. 3 and 25. The square root of 3 can't be factored out any further. So I'll just bring it down, get my leaves all highlighted, and I end up getting might as well bring those over too. For the 3 times the square root of 12, I end up getting 3 root 2 times 2 times 3. So I have a group here. I'll pull out a 2. So I have 6 root 3. And then I add my next set, pull out a 5. So I have 5 root 3 here. And then minus root 3. So notice now our indexes and our radicands all match up. Actually going to move all this over. Oops. So now we can just add or subtract the things out front. So we have 6 plus 5. Notice because there is not anything out front here, it's actually 1. All times the square root of 3. So 6 times 5 is 11, minus 1 is 10 root 3. And that is our answer. And then we can do the same idea with a cubed root. This time I'm actually going to find perfect cubes versus doing all of the factor treeing. Either is totally valid. But instead of doing all the factor trees, I'm going to start out knowing that I can take a 2 out of these, and that leaves me with the cubed root of 125. And that is actually a perfect cube. And I can take a 2 out of 54, and that leaves me with the cubed root of 27. And I can take a cubed root of 2 out of cubed root of 16. And that leaves me with the cubed root of 8. Now, cubed root of 125 and the cubed root of 27 and the cubed root of 8 are all perfect cubes. So we actually end up getting 5 cubed root of 2 and 3 cubed root of 2 and 2 cubed root of 2. So my indexes, my radicands all match up. That's good news for us because we can go ahead and finish solving. 5 plus 8 minus 2, all times cubed root of 2, will get us, oh, sorry, not 8. I don't know where I got 8 from. 5 plus 3. I did that in my head. Got 8. 5 plus 3 minus 2. That will equal 6 cubed root of 2. And we're done. Now, if you don't remember the cubed roots, we wrote a cubed root chart on a previous lesson. You can go find that on that lesson. Now, we also are going to be multiplying and dividing or rationalizing the denominator of these. This is just like foiling with just a few extra steps. So you do the first times the first, the outsides times the outsides, the insides times the insides, and the last times the last, just like a foil. Okay, so 4 times 5 is 20. 4 times 4 root 2, you just multiply these guys, you end up getting 16 root 2. Same thing with 2 root 2 times 5, you just multiply these guys, you end up getting, oops, not multiply, but plus 10 root 2. Probably the hardest of all of these is doing a root times a root. So 2 root 2 times 4 root 2. You just multiply each part separately. So we end up getting 2 times 4 is 8. And then that is times root 4, but root 4 is really just times 2, so this is 16 on the end. So this is probably one of the more difficult pieces of this FOIL. If you can combine like terms, as in our addition here, indexes and radicands match on these two, go for it. And combine just the whole number, so 20 plus 16 is 36. And 16 square root 2 plus 10 square root 2 is 26 square root 2 as our solution. We can do it again. Pretty simple, hopefully, after you do it once, to just do it again. You FOIL, so we have our first times our first, out times out, in times in, last times last, so 3 times 5 is 15. 3 times root 7 is simply just 3 root 7. Then we have that negative in there, so we need to take negative 5 root 7. And then we need to go ahead and take negative root 7 times root 7, which is just really negative root 49, which is equal to negative 7. Combine like terms. So we have 15 minus 7, which is 8, and then 3 root 7 minus 5 root 7, which is negative 2 root 7 as our solution. Okay? And then this last one, it looks a little different. Notice how the only difference between these is the sign between the whole number and the radical. That does something kind of cool, which we'll use in just a couple minutes later. Still FOIL though, we have 2 terms in each. So we need to use that FOIL method. So 5 times 5 is 25. 5 times root 7 is just 5 root 7. Negative root 7 times 5 is negative 5 root 7. And then once again, we do have the same last term, so we just saw this over here is just minus 7. Go ahead and combine like terms. Notice how these middle 2 terms cancel out. That's what we're going to use in just a minute. They go away. Then we have 25 minus 7 is simply equal to 18. And that is our solution. All right, so we got to use this part C idea on the next examples. We saw this idea when we used imaginaries. We couldn't have imaginaries on the bottom in the denominator, so we multiplied by something called the conjugate. We're going to use this again. Okay? So, we are going to use the conjugate to rationalize the denominator. That means there just won't be any radicals in the denominator. It's as simple as switching the signs. Then you FOIL, numerator and denominator. So I take, let me rewrite this, I suppose. That way it's easier to see. We FOIL first, outer, inner, last. Just go ahead and follow along. Once you see these a couple times, they'll become a little easier. And then this top is actually pretty easy because it's not a FOIL, it's just a distribute. So you distribute it to both pieces. You can finish it out. We actually can't reduce anything here, so we are good to go on that one. And this last one, we're going to do a very similar thing. It's just the conjugate again. So you switch the signs, multiply both the numerator and denominator by that. This guy actually reduces to simply 1. That's why you can do it, because if you multiply anything times 1, it's just itself. So we're reducing, rationalizing the denominator in that way. We have to FOIL. So 5 times 5 is 25, plus, minus 5 root 2, plus 5 root 2, and then negative root 2 times root 2 really just gets us negative root 4, which is negative 2. That is our last terms. Go ahead and simplify. The radical terms cancel out, and you are left with 23 in your denominator. And then go ahead and distribute in the numerator. So we get 15 root 2. Minus, now this one can be confusing too. You have 3 root 2 times technically 1 root 2, which is just 3 times root 4, or 3 times 2, which is 6. So you have 15 root 2 minus 6 all over 23 as your solution. All right. That is all I have for you today.